My name is Christine Harold. I'm professor and chair of the Department of Communication. I'm really glad to see all of you. It is my great pleasure to introduce Dr. Mitch Reyes, professor and chair of the Department of Rhetoric and Media Studies at Lewis and Clark College in Portland. I first met Mitch when we were graduate students together at Penn State, when flip phones were still improbably futuristic, at least for people like us, and we were all convinced that Y2K was going to be the downfall of civilization, and the White Stripes and Outcasts were in their prime. As it happens, Mitch and I were also both students in rhetoric and media studies at Willamette University in Salem, Oregon as undergrads. And so you know that his educational pedigree is impeccable because it's the same as mine. No, we didn't know each other as undergrads, but very much so as graduate students. So if you'll indulge me, I have just two quick memories that I'd like to share about Mitch that I think give a little bit of insight into the kind of person that he is. One is, over beers one night at Zeno's, which is a basement bar in State College, Pennsylvania, Mitch criticized Noel Gallagher of Oasis, who recently said that his band was bigger than the Beatles. Mitch disapproved, arguing that it was an incredibly arrogant thing to say, as well as shamefully untrue. I, while agreeing that Oasis didn't compare to the Beatles, or at least the jury remained out on that one, I argued that their arrogance was very rock and roll, and that John Lennon would have approved of their bravado. Mitch persisted because, ever the gentleman, he didn't like seeing a legendary band disrespected by upstarts. This was the way that Mitch always conducted himself in school, in graduate school together for 6 years. He was thoughtful and respectful, even when in disagreement. Two, might have also been over beers, Mitch patiently, but in vain, tried to explain to me the relationship between the philosophical tradition of the golden mean in Greek philosophy and rhetoric and the golden ratio in mathematics. This was around 20 years ago, and Mitch was already making connections between the art of rhetoric and the science of mathematics. In the intervening years, Mitch has continued to plow new territory in the field with his innovative perspective on our collective rhetorical practices, publishing multiple journal articles on rhetoric, mathematics, public memory, as well as 3 scholarly books, Remembering African Americans in America, An Epic Struggle with Difference, an edited collection entitled The Global Memoryscape, Contesting Remembrance in a Transnational Age, and his most recent 2022 book, The Evolution of Mathematics, A Rhetorical Approach. His talk today is entitled The Rhetorical Power of Mathematics in Contemporary Culture, Chatbots, Algorithms, and the Anthropocene. So I would like to, before I turn things over to Mitch, just remind everybody that we have a department-sponsored happy hour right after this talk at 5:30. You're all more than welcome. We would love for you to come have a drink, some appetizers. We'll be meeting down at the Mountaineering Club, which is on the top floor of the Graduate Hotel. So please do join us if you'd like to. So finally, just please help me to welcome Professor G. Mitchell Reyes.
Thank you.
Welcome, Mitch.
Thanks. Maybe we can argue about Oasis down at the bar after. That'll be great. Do we have any grad students in here by chance? Let me give you one of these. One of these. Grad students? Grad students? 3 for you. Grad students. There you go. Anybody else I missed? Grad students? Okay, so for everybody else, I have, you've already got one, so you don't need one of these. There you go. There you go. Yeah. Anybody else? Did I miss anybody? There you are. There you are. So these are just little cards about the book that I recently published with a picture on the back that looks nothing like me anymore. It's like, you know how you don't get headshots very often? So I just haven't gotten around to it, and it's getting pretty funny at this stage, so maybe I'll just keep going. At the end of the talk, because this book is so embarrassingly expensive, I do have one copy that I was going to raffle off to a grad student. So you got a number on that card of yours, every grad student does. And since there's roughly 10 grad students in here, I'll pick a number randomly out of 1 to 10 and give you a book. So that's all right. You have a number that's above 10. Yeah. So I just want to give a little bit of background, but first, thank you for inviting me here. I'm honored and really grateful to be invited and to get this chance to share my work. When I was first writing about rhetoric and mathematics, there was nobody in the audience. And a lot of people looked at me strangely, like, "What are you talking about? Rhetoric and mathematics? Have you lost something?" And so it's been an effort to sort of convince people in the field, people in academia, that there is something there in terms of the relationship between rhetoric and mathematics. And I'm happy to say that the rooms are filling up now, and more people are coming around to this connection and really how pervasive it is in our everyday lives. So I want to thank Leah Ceccarelli. I like people to be up here with me, so this is the way I'm bringing you up here with me, Leah, who I've always been inspired by her work. I've really appreciated her work and her service to the discipline. She was instrumental in helping me get this book to publication as the editor of the Transdisciplinary Rhetoric series at Penn State Press. So thank you, Leah, for all of your work, all of your great research. I also want to add a thank you to Christine Harold, who, like she said, had to put up with my esoteric theory babble for 6 years at college. So she should be allowed to be up here with me just for that reason alone. So again, thank you, Christine, for all your work and all your service to the field and your service to this department, sharing it. A little bit of a background on my work. As a young undergraduate math student, I was going through life with the same ideas about mathematics that most people have, which is that mathematics is a system of thinking that allows us to detect patterns in the world and patterns in the cosmos, patterns in the universe, and that those patterns are always already there, waiting to be discovered if just the right kind of mind comes along to think them and to express them in mathematical form. And so from that framework, mathematics is kind of very black and white, true and false. And I thought that that's what mathematics was. And a couple things happened in the last years of my undergraduate study, one of which is that I took this incredible rhetorical theory class from a great professor, David Douglas, who Christine also knows, who's the best pedagogue in a classroom I've ever seen. And he really opened my eyes up to the possibility of thinking of math not as a system that produces truths about the world, but as a language system that persuades us to see the world and engage with the world in particular ways. And that really changed my perspective, and it affected a kind of intellectual shift for me away from grad school in mathematics, much to the chagrin of my father, and towards graduate school in rhetoric, philosophy, semiotics. And that's really what I focused on when I was at Penn State. And that's the kind of stuff that Christine had to deal with for so many years. Fast forward a few years, 15-ish, and we have the evolution of mathematics, a rhetorical approach. And I'm happy to say my thinking about mathematics as a rhetorical symbolic system has changed quite a bit since I was writing those first articles in Pennsylvania. My favorite story about this book is that I was writing it when the pandemic broke, right? And I had a 4-year-old at the time. And if you know anything about kids, 4-year-olds have a lot of energy, a lot of energy, so much energy. And so, of course, he had to come home, and there's no way I could write in the house. But I couldn't go anywhere else either because it was the pandemic. Right? So what am I going to do? So I decided I was going to try to write in my Prius. So have you ever played the game of life? That huge board game? It's like, it turns out it's a pretty good desk. So I took the game of life from my home. I drove somewhere with a decent view, and I had my books in my passenger seat, and I wrote the second half of this book in my Prius during the pandemic. Right? And it was amazing. It was like incredibly productive. I wrote more in a few hours in my Prius than I seemed to be able to write anywhere else. So I dedicate half of this book to my Prius, to my son, and to the game of life. So that all brings us to the problem, the puzzle, the exigence. Every project has to have a puzzle, a problem, and exigence, right? And those problems, those puzzles, or those exigencies, they usually provide an opportunity. So what are the exigencies of this project? First, math is such a powerful means of argument and persuasion. And yet we as a field consistently ignore or run away from this means of argument and persuasion. And that seriously undermines our capacity to account for public discourse and public culture as it's changing. That's always been the case, but it's more the case now than it's ever been. And that's why I think rooms are starting to fill, because you just can't deny the incredible cultural force of mathematical discourse today. So that's problem number one. Problem number two, mathematics has become the meta-discourse of the social material world. By meta-discourse, I mean a hegemonic discourse, not in the sense of like ideologically hegemonic, but in the sense of hegemony as that which gives order to things. That which has the ontological and epistemological force to order the social material world. And it's that ordering of the social material world that helps me to understand the Anthropocene in the first place. I say social material world to underscore the unity rather than disunity of the social and the material, and to highlight how those two are being increasingly entangled with one another in the 21st century. I also say social material to underscore the inadequacy of both realist and constructivist paradigms for understanding math and, I would say, culture in general. To put a finer point on it, mathematical discourse in the 21st century, its ability to shape and constrain public discourse today has only increased exponentially. And so it's increased so much that I would argue the rhetoricity of math, which has always been there, cannot be denied or ignored any longer. We're going to have to figure out what the rhetoricity of math means, but we'll do that in a second. So when we say rhetoricity of math, I'm thinking broadly in terms of the way that mathematical discourse has enabled us to map the relations at the molecular level. So much so that we now talk about life as if it's written in code. That is a result of mathematics that took place 200 years ago. I'll show you why. Okay? I'm talking about a world where our relationships with machines and the differentiation between the mechanic and the organic is being so blurred that the differentiation no longer serves us very well for understanding contemporary culture. I'm talking about racialized algorithms that read faces and tell you who something or someone is. I'm talking about a planet that's being mapped and shaped and influenced by forces of big data that require incredible computational power. And that power has to come from somewhere. And despite all of this, rhetoric and communication scholars consistently ignore mathematical discourse. There's some reasons why that we can talk about, but there is a consistent denial of this incredibly powerful discourse in our daily lives. And a further problem, these mathematical architectures are becoming increasingly opaque to the citizens who even desire to understand them in the first place. There's all sorts of proprietary reasons designed into our capitalistic systems that causes that opacity. That's another problem. All these problems, though, they lead to an opportunity. The good news is that these exigencies create an opportunity for us as a field and as scholars to serve the much needed role of critical informant. Critical informant on these currently opaque but not necessarily opaque topics and discourses. And to inform our collective citizens about the social material force of these mathematical architectures. To do that, however, I argue that we first need to get a handle on what I call the rhetorical force of mathematical discourse. First, some good news. You do not need a math degree to do this work. Okay, so that's the first thing that we should cast aside. Oh, I can't do math, therefore I can't do this work. There are so many projects that need to be done that require nothing more than a high school level skill with mathematics. Casting that concern aside, what the heck does the rhetorical force of discourse mean? Well, not surprisingly, there are a lot of answers to that question, which is a good thing, because it means that people care about the question and have thought about the question, not just in our discipline, but in all sorts of different disciplines. The result of which is that there's actually a quickly growing literature asking questions about the social material force of mathematical discourse. Some of that has to do with the rise of algorithmic culture. Some of that has to do with the rise of AI. Some of that has to do with CRISPR machines that can suddenly sort of rewrite DNA and transform whole organisms in a series of a couple of life cycles. Nonetheless, there are an increasing number of interdisciplinary scholars that are interested in one dimension or another of what I think of as the rhetoric-math interface. So that's good news. I organize that literature into three constellations. The first I call the rhetoric of mathematics. Then this is what the earliest research into the rhetoric-math interface was interested in. And I'd even say a majority of research today is interested in this dimension, the rhetoric of math, which focuses here on the influence and persuasive force of mathematics in other domains, like politics or public policy or human behavior. So you can think of Kahneman and Tversky's work. You can think of the book Weapons of Math Destruction, which was recently published a few years ago. You can think of Deirdre McCloskey's work on the rhetoric of economics. You can think of James Wynn's work on the way that mathematics changed biology as a field. So these are all different ways of thinking about the rhetoric of mathematics, the influence and persuasive force of mathematics outside of mathematics proper. So not surprising, a large majority of this literature falls into this broad category and is generally interested in what I think of as the implementation effects of math. So that's about how to lie with statistics. That's about algo trading and the way that algorithmic trading is driving networks of power, funding the financial systems globally around the world. That's what that kind of work is focused on. And then, of course, there's the second category, the rhetoric in math. And this research is interested primarily in how mathematicians argue with each other, how they persuade one another within mathematical communities. So what is a compelling proof in mathematics? What's the kind of discursive or symbolic architecture of a mathematical proof? So you can think of Imre Lakatosh's famous book, Proofs and Refutations, as an example of this, and there are several others. The third category is the constitutive rhetoric in mathematics. So within rhetorical studies specifically, the above interest in argument within mathematical communities evolved with a little nudge from yours truly to consider, instead of just the way that mathematicians argue with each other, or how they persuade each other, or how they construct proofs, instead of just focusing on that, focusing on core mathematical ideas, ideas that have, on occasion, catalyzed a paradigmatic shift in the field of mathematics. And this was the focus of my first QJS article on the invention of the calculus. And it was about the invention specifically of the concept of infinitesimals and how the concept of infinitesimals really transformed the field of math and mathematical discourse. So sympathetic interdisciplinary work along these lines include Brian Rotman's semiotic approach to math, as well as Lakoff and Nunez's work, their cognitive metaphor approach to mathematical discourse. So that's a kind of a rough tracing of the sort of intellectual terrain and literature around this topic in different ways. So that's an image of the infinitesimal. The idea of the infinitesimal is you take a curve and you break the area under the curve up into smaller and smaller pieces, and the error, as you break it up into smaller and smaller pieces, crashes towards zero, right? And so this is the way that Newton and Leibniz first created mathematical models to track movement or rates of change through space. So all of this work, even my early work, eventually led me, after years of thinking about mathematics and doing this work and thinking about how ideas come about, thinking about how mathematicians argue with one another, thinking about the semiotics of math, or thinking about it from a metaphoric approach, I became increasingly dissatisfied with how far that got us in terms of understanding math's influence in the world. I became increasingly dissatisfied with how that was able or unable to explain how math has evolved and how that evolution of math corresponds with its social material force today. And those became the questions I wanted to pursue. So the problem is this: rhetoric as argument, persuasion, symbolic action, constitutive, what have you, is limited. And I had to get my head around why that particular perspective was limited, why I always felt like I came to a stopping point in being able to explain the profound influence and power of mathematical discourse in contemporary culture. So you might say, well, Mitch, what's wrong with these definitions of rhetoric as argument, persuasion, or symbolic action? And I would say, okay, nothing is inherently wrong with those definitions of rhetoric. But they do have a few important limitations. The first limitation is that these approaches tend to orient rhetoric ontologically around speech, whether in oral or written or visual form, which I argue has within it a kind of gravitational force that draws us, despite our best efforts, back again and again to a representationalist paradigm in which people speak or write to represent the world and or their ideas. This orientation towards speech is the root of the humanistic approach that has dominated the field of rhetorical studies for millennia, and that consistently centers human action and human agency, sometimes in explicit and sometimes in implicit ways. The second limitation is that the ontological orientation towards speech, or symbolic action more broadly, offers an originary bifurcation, in Western thought at least, between rhetoric and mathematics. Even Isocrates, that great champion of civic rhetoric, draws a sharp line between mathematics, at that time the study of geometry and number, and the truly valuable pursuits of rhetoric, right? The question of public affairs and making decisions in the polis and doing the work of self-governance. It's like Isocrates said, it's fine for you to sharpen your mind by playing with geometry, but don't get distracted, right? Because that's not really important. What's really important is this thing called rhetoric over here. So at the very beginnings of the Western tradition of defining rhetoric, that you can already see a line. And guess what Plato does? He carves that line even harder, right? And as you probably all know, we largely live in a Platonic world. Plato's influence is hard to overstate in the way that we think today. That's one of the things that I had to fight when I first started doing this work, is fight that bifurcation that we had also as a field sort of digested and kind of unwittingly, I think, accepted. So that bifurcation between rhetoric and math, I think, is a real problem. One result of this bifurcation is that early on, the work in rhetorical studies focusing on math seemed to be claiming, their main claim seemed to be saying something like, see, there really is rhetoric in math. As if that was the goal, to prove that persuasion and influence and human subjectivity really does exist in math. I don't think that that should be our goal in the study of mathematical discourse. And I certainly know that's no way to make friends with mathematicians. And being friends with mathematicians is actually kind of important for doing this kind of work. The third limit is that these approaches, rhetoric as argument, as persuasion, as symbolic action, fail spectacularly. The agent-centered anthropocentric approach that comes along with these forms of understanding rhetoric, while certainly fitting in many types of study, fail pretty fantastically when it comes to understanding mathematical discourse and practice. So why do these rhetorical approaches fail so spectacularly? To address this question, I had to go back and think quietly and deeply about what one does when one does math. I had to think and talk to my friends who do math about mathematical practice. And the first thing that began to emerge to me is that when one does math, like in the doing of math, that's the important part, not the results. Don't focus on the results of math. Focus on the practice of math. And in the practice of math, an agent-centered approach often fails simply because when one does math, one is not alone. And you don't get to do anything you want and be taken seriously. You don't get to say 2 + 2 = 5 and be taken seriously. You don't get to say that a triangle has 200 degrees and be taken seriously. Right? And what that points up to me is that immediately when you start thinking about the practice of doing math, you have to have a framework of distributed agency. You have to have a framework that makes space not just for a human agency, but for some kind of discursive agency too. Because when you do and think math, you're interacting with a discursive agency that enables and constrains. So that's one problem that I found when thinking about mathematical practice. And in fact, not only are there human and discursive agencies, but there are also non-human agencies at play in the doing of mathematics. And this characteristic immediately challenges an agent-centered humanistic approach. What we needed instead is an analytic approach that could account for the distributed agency of mathematical practice. Luckily, we have a lot of scholars in the field already that are trying to do this, that are trying to produce different models of distributed agency. So the work in new materialism is trying to do this in different ways. There's all sorts of interesting work about code and the way that code and computational force functions. There's all sorts of work on algorithms. There's a great book called What Algorithms Want. So there's all this work. It's happening. Right? So we're not alone. I'm not alone in doing this work and asking these questions. The second reason why I think these approaches fail to account for mathematical practice is that, simply put, argument happens in the middle of mathematical practice. Mathematical practice is, at least in part, the art of translating the world into mathematical formalisms, whether we're talking about number or geometry or topology, in order to reveal patterns and relations. And it's the conjectures about mathematical patterns and relations that animate arguments within mathematics. In this sense, to start with argument is to start too late in the process of mathematical innovation. We need an approach instead that hones in on how mathematical formalisms simultaneously map and translate the relations that constitute the mathematical problem situation. Now, I handed out a kind of model of what this looks like within mathematics. If you don't mind me borrowing this. There's a couple extra behind you. So what you'll see in this model, which I'm sure is flawed and I'm sure I'm missing something, is that in mathematics, we begin with the social material world 1.0. And we go through a process of taking a particularly focused and structured problem situation, and through embodied inscriptive practice, through inscribing, through diagramming, through accounting, through modeling, we slowly translate that question or that problem or that field within the social material world into various forms of mathematical formalisms. We use formalization. We use strategies of commensurability. Number is a great example of a strategy of commensurability. Something that takes the diversity and the heterogeneity of the world and transforms it into information. Notice in the word information, the word form is in there. Did you notice that? Because what mathematics does is it pulls out from that social material world the form, the formal characteristic. Right? Number is a formal characteristic of things in the world. And through processes of commensurability and selection and deflection, the particularities of difference in the world are translated into similarities of form. Again, number is a good example of this. The US Census is a great example of this, where we use a census to count all sorts of things in the body politic. And what does that counting do? It helps us to see relations between things that we couldn't have seen before. So before the census, we don't have any clear correlation between, say, the number of babies in the land and the amount of park space in cities. But after the census, we can start to see those connections. So we see those connections through the census. The census becomes a lens through which we see and understand and can grasp the world, precisely because it takes those differences in the world and turns them into a similarity of form. Does that make sense? Awesome. So what mathematicians do is they then, after that translative process, they demarcate a problem situation. A problem situation emerges. What is the relationship between the amount of park space in a city and the number of babies? That can be an example problem situation. And through structures of formal relations, they configure a problem situation, whether they're using topology or whether they're using number theory or whether they're using geometry or a combination of those things. Informal mathematics, so there's two kinds of mathematics. I shouldn't presume that you guys know. There's informal mathematics. That's the process of innovation and conjecture, right? Conjecture production in that. Then there's formal mathematics. That's the proving of conjectures. So this is a model for informal mathematics, not a model for formal mathematics, which is a whole different thing. So informal mathematics, so you produce a conjecture and then you test that conjecture over and over and over again until you think it is a robust and probably valid conjecture. What you're doing when you're testing those conjectures and producing those conjectures is you're testing the relationship between things in the problem situation. What's the relationship between land, between park space, and between the number of babies in the land? What's the relationship between the number of babies in the land and the quality of schools? What's the relationship between the number of babies in the land and the number of universities that exist in a particular space? So you can create all of these questions that allow for these connections between things that left alone would be very difficult to connect. So that's the power of mathematics. The power of number is the power to translate difference into similarity of the form. It would be wrong for us to understand that translation as reduction. A lot of times, people in our field and in other social science fields, humanistic fields, look at mathematics and they see reductionism, right? You've taken all this difference in the world and you've reduced it to the similarity of form. But that's not the point of doing math. The point of doing math is not to reduce things to a similarity of form, that's the first moment in doing math, which then allows for this explosion of new possibilities, new relations that you can see now, having translated the world into this similarity form, that you couldn't have seen prior. That's the world expanding power of mathematics. It's not that it reduces the world into some homogeneous form. It's that in doing that, it allows us to map the relations that constitute the social material world. And when we can map the relations that constitute the social material world, that gives us the agency then to recombine those relations, to play with those relations, and to produce new principles of composition that can transform and expand that social material world. Does that make sense? Kind of? All right. I'm going to give you a couple examples because it's kind of hard, there's all this crazy theory stuff. To maybe put these things on the ground a little bit. So our first exemplar. I want to use an accessible but still interesting example. And Descartes' translation machine is a pretty interesting one. Now the first thing to realize is this isn't a singular object, but the Cartesian coordinate system is in fact a network of ideas. And I'm just going to unpack a couple of those for you. First idea, and many people just accept this when they see this thing for the first time unconsciously. But what it's asking us to do is imagine number as space. Just think about it. A number line, that is a spatial metaphor, right? You're taking number, this sort of abstract idea of quantity, and you're putting it on a line, okay? So it's already getting us to see the world slightly differently. Not only is it asking us to see number as space, it's also asking us to see space as number. Right? And that's a novel thing that happened in the 16th century when Descartes created his Cartesian coordinate system. It's also asking us to accept the idea that geometric figures are objects in space, which is the assumption that Euclid made in his approach to geometry. Secondly, when we use the Cartesian coordinate plane, we see through it. And as a result, it functions as a translation machine when we use it. It translates the world, the problem, whatever we're dealing with, through the ideas that constitute it. It might be hard for you to believe, but mathematicians used to believe that negative number was not real. Can you believe that? We take negative numbers so for granted today that it's hard for us to understand that for 2,000 years of Western thought, negative numbers were thought to be not real, unreal, farcical, right? They actually thought that negative numbers threatened the status of mathematics as the language of the cosmos. Because at that time, with negative numbers, you could do things that seemed absurd to them, that seemed to be absurd. We're going to have to talk about and figure out why they thought negative numbers were so scary. So this first translation is a translation of number itself. Number from quantity and magnitude, because that's what number meant. Number meant magnitude. And so you can imagine an ancient mathematician saying, what could it possibly mean to have -2 olives in my hand? Right? It would mean nothing. It's absurd. And that's why it threatened the system of mathematics. How can you have -2 olives? Okay? So what Descartes' Cartesian system does is it renders negative numbers spatial and visible. And seeing is believing. Equally important, because of that second idea that geometric figures are objects in space, what this does is it enables the translation between geometry and algebra, which were two completely separate and disconnected branches of mathematics at the time. And because it can translate between algebra and geometry, Descartes was able to solve so many problems that no other mathematicians could at the time. And mathematicians are nothing if not pragmatic when it comes to solving problems. If you can solve problems with your approach, mathematicians will not necessarily accept the approach, but they'll accept that there's something in the approach that allows for you to solve those problems. And we mathematicians need to figure out what that is. Right? So they're pragmatic in that sense. Second translation then is between algebra and geometry. And this had profound impact on the kinds of questions that mathematicians could suddenly answer. The third translation, however, goes beyond the esoterics of mathematic communities. And it has to do with terrain and motion and weather. This Cartesian coordinate system could not only map geometric objects in space, but it could map all kinds of objects in space. And so all of a sudden, things like land begins to be thought of as number, right? Because what this does is it asks us to think of space as number. So one quick exemplar that I want to offer you has to do with the evolution of European cartography as an example of how the Cartesian coordinate system influenced European ideas of space and land and colonialism. And sometimes you write something better than you could ever say it. So I'm going to just read a short passage from my book that kind of talks about these issues. The European exploration of the Pacific in the 18th century offers a great example to underscore the profound ways in which mathematical discourse functions as a translative rhetorical force. When Laperouse first visited Sakhalin, or Sakhalin, which it was called at the time, in the Pacific Ocean in 1787, he was weak. He had no knowledge of the land, the navigable straits, or the points of danger. He was dependent on the native population for guidance. Yet, when Europeans returned just a decade later, they were stronger, no longer dependent on those same natives. What changed in 10 years? The modalities of number and calculation combined with the Cartesian coordinate system allowed explorers to extract and mobilize traces through the use of logbooks. And this is a picture of one of Laperouse's logbooks. Those traces, slowly and painstakingly gathered in faraway centers of calculation in Europe, enabled the production of navigational maps. Those maps facilitated flows of capital, extraction of resources, and exploitation of peoples. Through numbers and Cartesian coordinates and logbooks, Sakhalin was subsumed, along with many others, into a broad category of European cartography. In French, Pacifique Oriental. In English, the East or West Pacific. None of which names places as much as they did new relations of power we now call colonialism. And colonialism is in part a name for the desire to control at a distance. How to act at a distance on unfamiliar events, places, and people? Answer, to somehow bring home these events, places, and people. Numbers, Cartesian coordinates, and logbooks combine to form an apparatus that transformed the ragged, unknown coastlines of Sakhalin into the stable forms of East and West Pacific navigational maps. How? The inscriptions in the logbooks, through number and agreed upon system of coordinates, became immutable mobiles, which traveled back from Sakhalin to the centers of calculation in Europe, which then allowed European scientists to create simulacra, navigational maps, of what they increasingly referred to as the East or West Pacific. Those simulacra had a number of material consequences. They allowed Europeans to simulate their next exploration before ever leaving shore. As a result, those Europeans became less indebted to the peoples of Sakhalin and elsewhere for their safe passage. The heterogeneity of the peoples and places inhabiting these vast geographies became transformed into the stable forms of the simulacra. The simulacra, in tandem with other cultural forces, slowly translated the subjectivities of myriad peoples into the objectivities of East and West Pacific navigational maps. And finally, those objectivities could then be more easily located, extracted, and sold. And this is a picture of an early map, an early European map of what they called Sakhalin from the 17th century. And this is its 18th century cousin. You can see how radically different the spaces are, how much more numerically precise this map is, how much closer it is to our current mapping systems of this particular area. So what do we learn about mathematics here? First, math doesn't just discover the true patterns and relations of reality. It translates and transforms those relations. So mathematics doesn't merely reduce the world into a mathematical form. Instead, it translates that world so as to better understand the relations that compose that world, the understanding of which leads to the invention of novel recompositions and novel hybrids. East and West India maps are novel hybrids that emerged in this period, that actively expanded the social material world of the time, and in this case, functioned as an engine of colonial empire. It also underscores, this example does, how important it is for us to understand mathematics in light of the networks and relations it renders, the ways it simultaneously concentrates and conceals power, the means by which it translates the objects of its gaze, the productive metaphorical structures it uses, and who we become when we do math. It must, in short, be understood in its myriad rhetorical forms. So what are the takeaways for me from the Cartesian machine? First of all, math often does the opposite of what we're told it does. Math isn't the language with which God has written the universe, as Galileo once famously said. Right? Math is an incredibly powerful, maybe the most potent and powerful language, discourse, symbolic system we humans have ever created to expand reality. We just can't seem to leave it well enough alone. So math doesn't merely discover these hidden truths of the real. Much more interestingly, it's also an active multiplier of the real, and it can accelerate the world's differential becoming in profound, scary, and perhaps even beautiful ways. Second, math doesn't transcend the social, the cultural, the historical. It translates. Instead of transcending the social material world through what people refer to as abstract thought, thinking mathematically actually brings one closer to the relations that compose the social material world. And that bringing one closer enables all sorts of means to multiply and expand that world. So reality isn't a stable thing out there to be discovered, to be studied, to be revealed. It's a collective network of relations. And math is a potent symbolic ecology because there isn't just one math, there are lots of maths. So it's a potent symbolic ecology of relational transformation and expansion. Okay, you might be asking, how does math actually expand reality? How does that do it? How does it do it exactly? So let's consider another example. How are we doing this time?
We go till 5, so you can have Q&A after. Yeah.
Okay. I don't want to explode your brains, but I'm going to talk about imaginary numbers, okay? You guys ready for this? We're going to do imaginary. We're going to go a little quicker because I want you guys to have time to have questions, so I'm going to go a little quicker than, like, you know. As Christine knows, I always overproduce material and then I get through half of it, you know, as a teacher. That's my move, I guess. So imaginaries are the best exemplar that I'm aware of how mathematical discourse can expand in a dramatic way our social material world. So let me offer you a brief genealogy. And I want to do this because it's going to demonstrate how radically different mathematics is and how mathematical discourse is radically different than it was just a couple centuries ago. It's also going to show us how those changes correspond with math's increasing influence in the 21st century. And it's going to demonstrate that mathematical discourse's translative force can only be understood at the level of the vinculum. And the vinculum is a fancy word for relations, the relation between things. Okay? So the story of imaginaries. What are imaginary numbers, you might be asking? Well, the contemporary mathematical definition is simply this. I, standing for imaginary, equals the square root of -1. Okay? So what's the big deal about that? Well, what does the square root of -1 actually mean? Right? So if you think about the original meaning of square root, it is literally to take a square and understand that the root is one side of that square. So if you have a 4-unit square, the root is the 2 units on each side of that square. That's the square root. Right? So now imagine you're going to take the square root of -4. What is the square root of a negative space? It doesn't make any sense to mathematicians at this time. You might say, well, it's for -2. But -2 also doesn't make sense because you see the square root, and the square is a physical space in the minds of mathematicians at the time. Right? And the idea of squares and square roots, they represented the geometric object square and the geometric object line. That was the root of that square. Okay? So for a long time, this idea of taking the square root of negative numbers was absurd, just like negative numbers themselves were absurd to mathematics at one time. So the story begins with negative numbers. And the question is, what changed this perspective? Well, we have to go back to the Cartesian plane. And we have to understand how the Cartesian plane helped mathematicians accept the reality of negative numbers in the first place. And what we now know is that that Cartesian plane helped mathematicians think about number not just in terms of quantity and magnitude, but also in terms of space, moving away from an origin in both directions in a kind of symmetric form. And you literally can see how the Cartesian coordinate system makes negatives visibly real. So this is an early moment in the departure of mathematical discourse from the episteme of representation. Because all of a sudden, mathematicians had to accept the idea that number didn't represent quantity or magnitude, something one can see in the world, but that number could and had to be, in order to solve certain kinds of problems, also negative. Okay, so this is an early moment of mathematical departure away from that episteme of representation. And I argue it's that there's a correlation between how far mathematicians are willing to go away from the episteme of representation and the rhetorical force of mathematics in the contemporary world. Despite the fact that Descartes was quite innovative with regard to negative number, he completely rejected imaginaries as absurd. And in fact, he was the one to name them in a derogatory way, imaginary. Right? He's like, what are you guys doing? And again, many mathematicians were afraid to even touch imaginaries because it would be the end of their career. They wouldn't be taken seriously by other mathematicians if they played with imaginary numbers. So for many, many years, mathematicians did it in secret. Right? Isn't that fascinating that they would do this in secret? Mathematicians are kind of a strange bunch. So why did Descartes think so little of imaginaries? Because imaginary numbers didn't behave like real numbers. For instance, they don't adhere to a linear order of magnitude, moving away from an origin in both directions. If anything, they move cyclically. They move in a circle. Right? I'll show you that circle in a second. So they didn't behave like real numbers, and on top of that, you could use the square root of negative numbers to make all sorts of absurd mathematical claims and supposedly prove them. So they didn't understand imaginaries enough to figure out their potential. And as a result, imaginary numbers were marginalized for centuries. They were kind of known about, but if you wanted to be a serious mathematician, you didn't touch them. Until a guy named Leonhard Euler came along, who is amazing. Like, he wrote so much math, it's just like mind-boggling. It's like 1,900 proofs he wrote in his life. He wrote thousands and thousands of pages of math. It just oozed out of him. It's kind of beautiful. So how did Euler change the consensus on imaginaries? Well, interestingly enough, this is a rather rhetorical moment in the history of mathematics. Because what Euler did is he introduced a new discursive transformation. He fabricated, by which I mean he constructed, the equality I equals the square root of negative 1. And that equality turned out to have tremendous rhetorical force, unleashing a potential expansion of the real in mathematics, the likes of which we have rarely seen. That potential was quickly realized in Euler's most famous equation, e to the pi I plus 1 equals 0. Now, I'm not going to dive into what that means right now because there's a chapter on it. Okay, and I don't think you guys want me to go into like the relationship between geometry and trigonometry and logarithms, and it's a lot. But it is a beautiful, beautiful equation. So why is this equation so important, and why does it make imaginaries more real? For one, it elegantly connects a myriad of different branches of mathematics that had previously been disconnected. Right? So it creates this network of relations between geometry and trigonometry and algebra and logarithms, and it therefore reveals this hidden connection that mathematicians previously hadn't seen. More importantly, it places imaginaries at the center of that mathematical insight. To put it bluntly, without I equals the square root of negative 1, Euler can't make this connection. So quite literally, it's the connective tissue that I provides that allows Euler to see the connections between logarithmic, between geometric, between trigonometric. Okay, fine, Mitch, neat, esoteric math, cool. How do imaginaries become materially manifest in the world, though? How do they change the structure of the world that we now live in? And I'm telling you, so much of what is in this room depends on imaginary numbers. So in order to understand that, we have to make one last return, I promise. This is the last time I'm going to ask you to look at the Cartesian coordinate system. But we're going to look at it a little bit differently. Because what emerged in the wake of Euler's fantastic mind and all of his fantastic work, well, a lot of things emerged. But one of the things that emerged is this really innovative blend between the Cartesian plane and imaginary numbers. And we call this the complex plane. But what does this blend mean exactly? In other words, just like with the Cartesian plane, when we see through it, we access and understand the world in particular ways. So when we see through the complex plane, what changes, what shifts? First, just like the Cartesian plane, we have to note the power of the visual. Just like the Cartesian plane helped make negative numbers real, this complex plane helped make imaginaries more real. More importantly, though, we talked about how imaginaries move in a kind of cyclical style. This is a pretty good representation of that rotational movement of imaginary numbers. So imagine you take the square root of -1. What happens when you square that number? The square root of -1. It just becomes -1, right? What happens if you cube that number? What does it become? It becomes -1 times the square root of -1, which is -I, right? Because we know that I equals the square root of -1. So it's -1I, or I, -I, right? So you can see how I squared equals -1. So I squared, I cubed equals -I. I to the fourth is 1, and it goes in that circle cyclically like that forever and ever. Okay? Well, why does this matter, Mitch? I mean, okay, neat, but so what, right? Well, it turns out that movement in a cyclical form is kind of useful to be able to model. Think about ocean waves. Think about how ocean waves move from an origin forward, but they also rotate, right? If you have a mathematical system that can both do rates of change and motion out from an origin and cyclic motion at the same time, you have a much more powerful model for mapping all sorts of phenomena in the world. Your ability to map the complex relations of movement both out from an origin in a vector way and their cyclical movement simultaneously, now you can better produce relational maps of that phenomena. You can predict its movement. You can see what's happening. You can even measure the force or energy inside of the movement of a wave. And not just ocean waves, but water that hits an object going down a stream. Imagine bridges and bridge building and how much force and how much wear and tear. You want to know how much force and wear and tear is going to be on that beam. Right? In order to model that, in order to create a powerful simulacra of that particular physical object, you need a mathematics that can do both movement out from an object and cyclically, right? Because when water hits that pillar underneath the bridge, what does it do? It swirls, right? And it's the same with electromagnetism, which moves in a wave-like system. Only recently do we know it's also particles. But early on, it was understood as a wave-like phenomenon. The whole electric revolution doesn't happen without imaginary numbers. The computers that you're touching and holding, the ones in your pockets, those don't exist without imaginary numbers. Our whole technological mass media system completely dependent on imaginary numbers. And if that's not enough for you, we wouldn't even begin to understand the quantum realm without imaginary numbers. So the translative force of imaginaries is pretty difficult to overstate. And here we see an image of electromagnetism in its wave-like formation. Here we see an underwater picture of a churning wave. And you can see and you can imagine how it's moving away from you, but also rotating like that. How do you create mathematical models that can handle that kind of dynamic movement? You have to have imaginary numbers. Without it, it's pretty impossible. So what do we learn from all this, and what about some future projects that I see coming at us? First, we learn that math is really about reality expansion. It's not simply about discovering the truth or true patterns in the world. I mean, it is about that, sure, but that's not all that it's about, and that's not really where the translative rhetorical force of math comes from. It comes from the reality expanding power of mathematical discourse. Mathematical discourse has profound capacities to make things real, not just study what's always already there. And rhetorical scholars can and should study this mathematical discourse because, frankly, mathematicians don't want to. They want to do math, okay? So they're like, that's interesting, Professor Reyes, but, can we go do math now? So they're not really that interested in these. That's not every mathematician, but most mathematicians just want to do math. They don't want to think about these things. In terms of future research, there's a few ideas of 1,000 that I could come up with that I think we as a field could look into and do research around. One is math's translative rhetorical force and the unraveling of democratic culture. And I'm not just talking about things like gerrymandering. I'm talking about how learning algorithms that are designed to optimize click-through behavior are destroying democracy. And the reason that they're doing that is because these learning algorithms learn about us. And one of the things they learn about us is that if we have more extreme political values and beliefs, we're more predictable in our click-through behavior. And so they will slowly feed you slightly more ideologically extreme views and content to push you, to nudge you farther and farther into the extreme of whatever ideology you already hold, thereby exacerbating the problem of polarization in the body politic. This is not just something that I've written about or thought about. This is something that a lot of people are worried about at a kind of interdisciplinary level. It's a huge problem. If we keep designing learning algorithms for object-oriented tasks like click-through behavior, we are going to destroy ourselves. So that's one project, I think, that's really important. And that kind of learning algorithm phenomenon, I mean, it makes the power of gerrymandering look childlike by comparison. The algorithmic architecture underlying ChatGPT and OpenAI. I mean, this is here with us right now, right? We're having to have these conversations with our children, with our students, at the level of academic institutions all over the country because of the power of these architectures. And one of the things that I haven't seen in all the discourse about ChatGPT is a question about the underlying algorithms that are functioning and driving this machine. Of course, they're proprietary. But that doesn't mean you can't pierce the veil. I find this picture particularly interesting, right? As if it seems to me, at least, that they're trying to project this idea that you interact with ChatGPT and they're therefore like some sort of higher way of thinking through that mutual work takes place. That doesn't seem to be the way ChatGPT is being used. Not to mention the fact that they're using cheap labor in Africa to clean their data. And I'm really interested in thinking with you all about this idea of agential inversion, or how we can make math more actively anti-colonialist, racist, and extraction capitalist. Mathematics has long been used in service of these large sociocultural formations in ways that I at least don't really love. And I think mathematics can be made to do something radically different than it's been made to do at this point, but only if we start asking the questions about the transitive force of mathematics in the social material world. So that's my work. Thank you.
Thank you.
Yeah.
So I guess my question is, does the world, like in your graph and in your talk, right, like both of the things you set up were about like sort of math representing or something in the world, or maybe or expanding the world.
Mhm.
Both of these require the world. Does
Mhm.
the world
The world is required.
the world is required.
Mhm.
So what about, I mean, like, I'm thinking of like results from number theory that seem to actually be about math. Like a lot of math is about math.
Mm-hmm. Mm-hmm.
So, and maybe this is sort of like a pure math versus applied math distinction. Is this a theory of applied math, or is this also a theory of pure math, or is that distinction not one that you? And you said there are two kinds of math.
Yeah,
there
there's
are also two math departments in this university.
Yeah.
They're not the two that you described.
Right, they're pure and applied, right. Yeah, so within the university and within mathematics, people will often differentiate between pure and applied mathematics. I think that differentiation is porous, at least. I do think that there's a world. Math is not arbitrary, right? You don't get to just say anything about the world that you want to with math. And math as a language also constrains us from saying particular things subject to the constraints of that particular language. Like you can't say 2 + 2 = 5, so that doesn't make any sense within that number system. So what I'll say is, and I didn't really get into this part of my work, is that mathematics, the agencies within mathematics are at least threefold. They are the world, which when they're thinking about a particular problem, takes up a certain kind of mathematical formalism to try to represent what's in the world, right? And then if they're good at mapping that particular problem situation, then they find certain patterns that exist within the world, within the relationships that make up that particular field, right? So you begin with the world. You map those relations, but you don't stop there. And this is where I think you go from interacting with and thinking about and representing the world to looking at the mathematics, pure mathematics, right? And looking at how you've distilled and translated that problem situation into mathematics, and then playing with the mathematics. And what you're doing when you do that is you're reconfiguring the relations that were originally in the world, right? And so when you do that, you, on occasion, rarely, look, most math is failure. But on occasion, rarely, you come upon a relationship mathematically that wasn't in that original system, that material world, right? And that enables you to then reconfigure that world in profound ways. And I think imaginary numbers is kind of a great example of that, because you start with Descartes' desire to create a machine that can translate between geometry and algebra. It's basically what he wanted to do. And he couldn't have foreseen the way that was going to be taken up and made use of by imaginary numbers, right? So his translation machine that he created allowed us to think about number as space for the first time, rather than in terms of quantity and magnitude, right? If you just stay in the world, number is always quantity and magnitude. As soon as you create translation machines that allow you to solve different kinds of problems that don't come at least directly from the world, you start to move in ways that expand the possibilities of the systems, the networks of relations that compose the world. And to me, reality is nothing more and nothing less than a networked system of relations. Yeah, so that's kind of, I don't know if that answered your question. Yeah. Yeah. Yeah.
So you started out by saying traditional rhetoric doesn't really help to get at all of this because it's too agential, it's too focused on words and visuals. But then the story you tell us, you know, we have these agents, Descartes.
Yeah, sure.
And then we have things that I would think of as sort of traditional rhetoric. Metaphor, right? We think of space as numbers as space and space as numbers. We see it. We're able to visualize something that we couldn't visualize before. I'm just wondering, maybe traditional rhetoric still has a place.
It does. And I try to make that argument explicitly in the book, that it's not about leaving traditional rhetorics behind. What I argue is that, in fact, I think it's the most robust analytic approach is to layer these forms, these ideas of rhetoric on top of one another and use them all kind of simultaneously. The point that I wanted to make there is that when we start with argument or persuasion or symbolic action, we run up against the problem that mathematics isn't just argument or persuasion or symbolic action. It's also the translation of the relations that make up the world into mathematical form. So if you want to understand that aspect of mathematical practice from a rhetorical perspective, you need a rhetorical theory that kind of attends to the relational, that attends to the way relations can be translated. And so my theory of translative rhetoric, which I didn't dive into at all here, that theory is about trying to create that different sense of rhetoric that'll let us get a little bit farther, I guess. So it's not to say that those traditional approaches aren't useful. They are, and they can answer all sorts of questions about math and public spaces, math and public argument, those kinds of things. But I don't think they take us far enough in terms of understanding the social material force of mathematics and contemporary culture. For me, you have to have that relational element to really understand that. I saw your hand last time, and then.
I would prefer to have a back with you.
Okay.
I guess just sort of related to that, when you give the examples of like algorithms or the map example, both of those I imagine like there's a, for lack of a better word, like a rhetoric behind those. Producing the algorithm or creating something out of the mathematics. So in both of those, it's the mathematician who's using mathematics rhetorically. Is there a way that you would imagine there's some rhetorical side to mathematics which doesn't have the mathematician there as rhetoric, either using or producing the rhetorical element?
Yeah, so it isn't just a model in which the genius mathematician stands behind the scenes and is kind of using their genius of reason and mathematical ability to generate new math. The model that I think of, this because that's not a very distributed agency model. That's a very sort of humanistic paradigm for understanding mathematics. And so what I would suggest is that we need a distributed model of agency where there are human agents, but there are also discourse itself. The mathematical discourse itself is an agent. It's an agential force. And we find ourselves, even the best mathematicians find themselves responding to that agential force. So, for example, the concept of the infinitesimal that Newton and Leibniz created, that created an incredible firestorm of controversy in mathematics and science at the time, because there wasn't the bifurcation between math and science when Newton and Leibniz were writing. And they had to respond to those criticisms. those criticisms came from other mathematicians that were saying, like, what the heck are you guys doing? Right? You can't break a space up into infinite parts and then just ignore the error. That's not what we mathematicians do. And the fact that you're splitting this space underneath the curve into infinitesimal parts, are those infinitesimal parts equal to 0? Are they larger than 0? Can we, if you break them up small enough, how small is enough before we can call them 0? So all these kinds of questions, right, were coming from mathematicians of the time because the concept of infinitesimal, it violated the standards of Euclidean geometry. And so my argument is that the infinitesimal itself has its own rhetorical force that the mathematicians and scientists of the time had to respond to. Just like imaginary numbers had their own rhetorical force, right, that mathematicians and scientists at the time had to respond to. Right? What the mathematicians and scientists couldn't deny is that Newton and Leibniz could solve all sorts of problems that nobody else could. What the mathematicians couldn't deny is that Euler could solve all sorts of problems with I that nobody else could. Right? But Euler couldn't see the potential of I to turn the world into this. There's no way he could see that. Newton couldn't see the powerful potential of infinitesimals to sort of be a generative force of new mathematics in all sorts of ways. I mean, we don't have any math beyond calculus until imaginary numbers come along. Then vector spaces happen. Then vector calculus happens. Then linear algebra happens. Then Fourier transforms happen. Then like the electrical revolution happens, you know? Like we can't map any of that stuff without I. But that doesn't mean that those things were always already there, waiting to be discovered. Yes, they were, and that mathematical modeling produces principles of composition. We understand the composition of relations within the world better, and that allows us to recompose and decompose those relations. And it's the decomposition of those fundamental relations in the ecology that helps me understand something like the Anthropocene. Like we're not here. We're not a full force of cultural evolution without the capacity to decompose the relations that were already there in nature, as it were.
Well, can you join me in one more round of applause for...
Thank you.